In this screencast, we're going to look at problem 30 of chapter 10 in Solomon's 11th edition of Organic Chemistry. So this question asks us to provide the reagents necessary for the following synthetic transformation. So as a general strategy, what I like to do is look at the starting material and the product and write down what the major functional group is in each of these. So we're starting off with cyclopentane, so this is an alkane. And we're ending up with this dibromide. So notice that it has a specific arrangement of the bromines. So they're in a 1-2 relationship and they're trans. So this is a trans Vicinal dibromide. So the other strategy that I like to take is to determine the molecular formula for both the starting material and the product. So we're starting off with cyclopentane, so that's C5. Then we count up the hydrogen, so each carbon has 2, 4, 6, 8, 10 hydrogens. Our product has C5, so the carbon count is not changing. Hydrogens, we have 2, 4, 6, 7, 8, and 2 bromines. So overall, from starting material to product, what we can see is we're substituting 2 hydrogens for 2 bromines. So in this type of problem, it's easier to work backwards in a retrosynthetic manner than to work in the forward direction. So what we mean by that is we're going to look at our product and then work backwards to get to the starting material. So the retrosynthesis arrow that we use is this double-headed arrow here. So we're thinking backwards at this point. So the reason why I want you to name the major functional group of the product is that's going to clue us into how we can make that. So we're ending with a trans vicinal dibromide. So remember, vicinal is 1-2 relationship relative to each other, and they're in a trans. So where does a trans vicinal dibromide come from? Well, that can come from an alkene. So that's going to get us back to our alkene. If we treat that alkene with molecular bromine, Br2, that's going to get us the trans vicinal dibromide. So that's the forward direction in that sense. So now we're at a simpler molecule. We're in an alkene. So our ultimate goal is to take this alkene and get back to the starting material. So notice the difference between this molecular formula and this molecular formula is C5, H2, 4, 6, 7, 8. So this molecule has 2 degrees of unsaturation. This molecule has 1 degree of unsaturation. So how do we get back from this alkene? Where do alkenes come from? So in our retrosynthesis, we learned a reaction that alkenes can come from the dehydrohalogenation of an alkyl halide. So if we have an alkyl halide, say bromine, we can treat that in the forward direction with a base, say potassium tert-butoxide. So that's going to do a dehydrohalogenation where we deprotonate this hydrogen and eliminate bromine to get the alkene. So this is going to be an alkyl bromide. And the molecular formula of this is C5, H9Br. And so it's up to us to take this alkyl bromide back to this alkene, so our retrosynthetic arrow. So how do we take an alkene and transform it into an alkyl bromide? Well, what we learn in this chapter is a radical bromination. So we can treat with bromine in the presence of light. It's our radical initiator. And that's going to do a substitution of one hydrogen for bromine to get us our alkyl bromide. So moving forward in the forward direction and writing the reagents, step 1 is going to be molecular bromine with a radical initiator of light. Step 2 is going to be our dehydrohalogenation with potassium tert-butoxide. And then finally, step 3 is going to be treatment with molecular bromine only. So notice there's no light in this case. So that's going to take the alkane to the alkyl bromide, to the alkene, to the vicinal dibromide. So this has been a screencast on multi-step synthesis, demonstrating the reactions learned in the radical halogenation chapter.